Assalamu alaikum. Dear students, last time we were at this point. We were looking at the meaning of the weighted values on a graph. So remember, these were the values showing, for example, we suppose that this is showing the distance between Austin to Dallas and from Dallas to Austin, and this is a two-way road going from Austin to Dallas and coming back from Dallas to Austin. So these values have some meaning among the relationship of these two nodes. Similarly, this Chicago is having value 100 towards Denver. It may be the distance between Chicago to Denver of 1000 kilometers, and of course there is a road back from Denver to Chicago of 100,000 kilometers as well. Similarly, from Washington to Dallas there is a road of 1300 kilometers, for example, and there is no road back from Dallas to Washington. So we can make these graphs, annotate these graphs with different values according to our need. Okay, then next is how we can implement these graphs. Till now we have learned the terminology of the graphs. Now we will see how we can use our learned data structures to implement these graphs. First we will look at the array based implementation. 1D array is used to represent the vertices, and a 2D array, adjacency matrix, it's also called the adjacency matrix, it is used to represent the edges. These are the, remember, edges, these lines, and these are the vertices. So while implementing this graph using the array data structure, we use two arrays. One is one dimensional array and the second type is the two dimensional array. So one dimensional array, with the help of one dimensional array we draw the vertices, and with the help of two dimensional array we draw the edges, their relationships. How? It should be like this. For example, if we keep in mind the previous graph, we have 7 places or 7 nodes, namely Atlanta, Austin, Chicago, Dallas, Denver, Houston, Washington, and there were multiple connections. So while looking at the connection, looking at the vertices, we draw this adjacency matrix. It is a two-dimensional 2D array, and we put on the values in this particular data structure. So at 0th index we have Atlanta. At index number 1 of this array we have Austin, Chicago, Dallas, Denver, Houston, and Washington. Okay, and now we have a 2 dimensional array of say 9 by 9 or 10 by 10, 0 to 9. So 10 by 10 array, and we now put on the values. For example, this 0 is connected with this 800, value 800. It means this one is connected with the 5th. So 5th is which one? This one, Houston. It means the Atlanta is connected with the Houston, and number 6th is Washington. It's also connected with Washington. Okay, this one. So with Atlanta is connected with this Houston at value 800, and there is an edge going from Atlanta to this Washington with value 600. So if we look at the previous slide, Austin is connected to this Dallas and Washington. Austin is where? Okay, this one is, oh sorry, Atlanta. This is not Austin but Atlanta. It's connected with this Washington 600, and Houston, Atlanta to Houston is 800. Similarly, the Austin will be having two connected values, Austin to Dallas 200 or Austin to Houston 160, like this one. Austin is at 1, so it is connected with this 3. So 3 is Dallas, so Austin is connected with this Dallas with value 200, and Austin is connected with this 5th Houston with value 160. Alright, so all will be draw like this one. So Atlanta has two connections, this Austin has again two connections, this Chicago has one connection, and so on. So this table is basically showing us which node is connected to whom and what is the connection value or what is the value of the edge. Alright, so these dots and array positions marked with dots are undefined. So these are the undefined region, or these are zero values, means Atlanta is not connected to Atlanta, Atlanta is not connected to Austin, Chicago, Dallas, Denver, but it is connected to Houston and Washington. So similarly, for other nodes we can make this these connections in order to make the relationship between this nodes and edges by using the array data structure. Okay, alright. The second implementation could be the linked list implementation. A 1D array is used to represent the vertices. A list is used for each vertex V which contains the vertices which are adjacent from V, that is the adjacency list. Now in this case, keep in mind this graph again. So keeping this one, we will use one dimensional array to use to represent the vertices, these vertices, and we will use a linked list for these connections, like Austin is connected to Dallas, Austin is connected to Houston. So the node of Austin will be having two further nodes in the form of linked list, one to the Dallas and one to the Houston, like this one. So if we look at this one dimensional array, or it could be a single linked list, and this is the data part, this is the node part. So we have a single linked list of 7 nodes representing the nodes, all the nodes, Atlanta, Austin and Chicago, Dallas, Denver, Houston and Washington. Atlanta is connected with this 5 is this one, Houston, with the value 800. Again the Atlanta is connected with this number 6, which is the Washington, and the value of connection is 600. Similarly, Austin is connected with this 3 is what, Dallas, with value 200, and Austin is connected with this 5, that is the Houston, with value 160. And then Chicago is connected with this 4, Denver, or Chicago is having the link or the node vertex value, edge value is 1000, and same for the other nodes. So this is the linked list implementation. On the one side, it is containing the nodes for all the available destinations, and then there is a linked list for all the connections from that particular node. For example, from Atlanta we have 2 connections, one is with the 5th, which is Houston, one is with the 6th, which is Washington. Atlanta to Houston is 800, for example, kilometer. Atlanta to this Washington is 600, for example, kilometer, and so on for the other. So if we are given with a graph, we can easily depict that particular graph into the data structure. Either it is a linked list based implementation, or it is a array based implementation. Okay, then there are different searching techniques from the graph. We for example, there is a problem, we want to find a path between two nodes of the graph, for example Austin and Washington. So if we need to find a path, remember the definition of the path. If we have multiple edges connecting from one node to the destination node, it means there exists a path from that node to the destination node. So different methods can be used. One is the DFS, which is the depth first search, and the second one could be the BFS, breadth first search. So two methods are there in order to find a path between two nodes of a graph. So how DFS, depth first search, works? What is the idea behind the DFS? Travel as far as you can down a path. For example, start from one node and start traversing or traveling as long as you can travel. Back up as little as possible when you reach a dead end, that is next vertex has been marked, or there is no next vertex, means start from one point, keep going until you find a dead node, or you find some node which has no out degree or no out arrow, and then slightly back and find the other path. DFS can be efficiently implemented using a stack. This is the algorithm of depth first search. DFS: set found to false, stack.push start vertex. स्टैक के अंदर हमने जो स्टार्ट वर्टेक्स जिससे सर्च शुरू करनी है उसको पुश ऑन कर दिया, एंड देन देयर इज अ लूप डू वाइल डू स्टैक डॉट पॉप वर्टेक्स. If vertex is equal to end vertex, the one we want to found, set found to true, else push all the adjacent vertices on the stack. We know what is the definition of adjacent vertices by now, that all the nodes which are reachable from that particular node, which is the start vertex in this case for our. So all the node put onto the stack, while not stack is empty and not found. The loop will keep continuing until the stack is not empty or we have not found the vertex. So finally, if not found, then write path does not exist. If there exists some path, then that will be traced at this loop and that will be shown. For example, look at this graph and we want to find the let's say Washington, and our start node is the Austin. So the algorithm says, first of all, push that start this particular node to the stack, and found is set to false. Next we have to push on the stack all the adjacent nodes of this Austin. So Austin, first we according to the algorithm popped the value which is the on the stack, which is Austin, and adjacent to the Austin they have been pushed to the stack. So which are the adjacent to the Austin? One is the Dallas and second one is the Houston. So pop Austin, push its adjacent values, which is Dallas and the Houston. Okay, so the found is because the end vertex to be found is the Washington, so it is not found yet. So the loop will iterate one by one. We will pop from the stack we will see either it is a destination node. If yes, then break the loop. If no, then we will push the adjacent of that particular node to the stack and keep continuing. So in this case, we pop the Houston. Houston is here, so Houston is not the destination. So what we do is we push the adjacent vertices, adjacent nodes of this Houston to the stack. So which are the adjacent nodes of this Houston? It is only Atlanta. So Atlanta has been pushed onto the stack. Dallas is already there, so it is not yet popped, but the Houston is popped. It is not the destination for, so we just put or push the adjacent nodes of the Houston to the top of the stack, which is the Atlanta only in this case. So next we pop the top of the stack, which is the Atlanta, and we found that it is not the destination, so we just pushed the adjacent values or adjacent nodes of Atlanta to the stack. So adjacent node of the Atlanta or the this Washington. There is also adjacent node Houston to the Atlanta, but that has already been traversed, so we will not consider this one. So Atlanta is only left with this one adjacent, which is the Washington. So Washington has been pushed onto the stack. Okay, so next we pop operation returns the Washington, and Washington is our desired or our destination node. So that sets the loop value, a found value in the loop, to the true and break the loop. So once the loop is broken down, the path path will be displayed. It means we have found a path between one node to the destination node. So what is the idea behind breadth first search? We just discussed the DFS, depth first search, and now we'll look at the breadth first search. So the idea behind BFS is look at all possible paths at same depth before you go to deeper at that particular level. So back up as far as possible when you reach a dead end, that is the next vertex has been marked and there is no next vertex. So this is the algorithm of this breadth first search. So please try to execute it and try to implement it and try to understand this one as we did for the DFS, the previous algorithm, depth first search. This is the implementation examples of the previous BFS algorithm. So please try to map the algorithm with this example and see how this DFS works. So this is the algorithm continues, and this is the code written for you. You can implement it as well. First you need to understand the concept with the help of graph and with the help of animations provided to you, and then you can implement the idea by using this code. Okay, there is a single source shortest path problem. There are multiple paths from a source vertex to a destination vertex. For example, from one city to the other city or one node to the other node, as we have seen in the previous example, there could be many paths exist, but the shortest path is the path whose total weight, that is the sum of edges, is minimum. Means we want to reach from one node to the other node by using the minimum traveling, for example. So keeping in view the previous graph, we have example of Austin to Houston to Atlanta to Washington concludes 1560 miles. But on the other hand, Austin to Dallas to Denver to Atlanta to Washington results in 2980 miles. So which one is shortest? In this case, the first one. So that is the shortest path between Austin to Washington. So that is called the single source shortest path problem. So common algorithm to find this is the Dijkstra algorithm, Bellman-Ford algorithm. BFS can be used to solve the shortest graph problem when the graph is weightless or all the weights are the same. BFS can be used to find in case when the graph is the weightless. Otherwise, we need to use the Dijkstra and Bellman-Ford algorithm for finding the single source shortest paths. You may learn in detail in the course of algorithm analysis that how we used and implement the Dijkstra and Bellman-Ford and many other algorithms, but for the sake of this course we just confine ourselves to the understanding of the graphs, and then we see the implementation of the graphs by using the data structure, and then searching of different nodes or traversal between different nodes. So okay, there is an exercise for you. Represent the following graph using array and linked list. So please consider this graph which is having 5 nodes. So you have to represent this graph by using the array data structure and the linked list data structure. So please make these mapping of this graph by using the array data structure, the one we have seen in the previous lecture, that there will be one single dimensional array and there will be one two-dimensional array, and we will see which one is connected to which one. And same work has to be repeated with the linked list data structure. So please make both of the implementation and send it to me via the WhatsApp group.